it's not that I am trying to be deliberately, dragging you through a whole bunch of different things, but implicit differentiation is in the 4-unit. It's hidden away there, but it is there. It's a bit obscured. Okay, so when we come to do partials, so it's just nice to have that map, I think, just to have that map so that you know there's different things, horses for courses. Alright, so enough of that. I'll put that out of the way, and let's have a look at our version of partials. Alright, so for tute 3, I think we're fairly straightforward. So we've got A is a two-valued function, and you can plot these if you want to see what they look like geometrically. 2x2 minus 3xy plus 4y squared. So implicitly this would be a different beast. To implicitly differentiate this, it would be a difficult proposition. All right. So in terms of doing our function with respect to x in terms of partials, and another way of writing that is to put the lower subscript x on a big function, and so that would end up being the same thing. Now we can still use technology. Again, I'm going to show you this. Sorry to pop this up again, but in the modules, so that's all that stuff, so that's good. And then we've got some know-how. So the two things to get from here are the informative examples from Wolfram Alpha. We'll just have a quick look at that, but also worked examples from the examination pool. Now that's not for us, that's for, oh well, it kind of is for tutes, I guess. So we'll have a quick look at both of those. The worked examples allow you to go and have a look at this. Alright, so if you wanted to have a look at the chain rule one, when you click on the chain rule, it'll open up this one. So there's heaps in there. I don't know if you've had a chance to, and in fact what I say to my students is pretty much we don't do exams in this subject, but if I do an examination it's going to be taken from questions from there here. So often that happens at university. The stage 1 and stage 2 teachers, maths 1 and maths 2 teachers, calculus 1, calculus 2, and to some degree this one, will take examination questions from a textbook. And there's nothing wrong with doing that. But I've given you a large number of resources, I think, from past papers, so you can do that. And the other thing was the informative examples. So it'll do the partials for you, just working out which ones of those commands. If you play around with that, you can do the partials that way as well. It's always too much info, isn't it? All this stuff that you can wade through, and there's never. I have the same problem. Don't worry. There's never enough time in the day to get everything done that you want to do. All right, so is anybody so what are we doing? We're looking for doing everything with respect to x, and it also wants us to do y, because it says all of the partial derivatives. So in this one here, we've got, if we come and just focus on x, and the difference between what we do here and implicit is we treat the constants as though we treat the other variable, the one we're not doing, as if it's a constant. So let's just, what does it mean to differentiate a constant? Okay, so we end up with a 6. One comes out the front, one off, we end up with, in other words, the constant remains. So it doesn't matter what the form of the differential is. Okay, what we'll get there is we've got two constants, and so the two constants will remain and the x will disappear. Okay, so when we do a d dx of one like this, that's just the same as these over here. We treat the y as though it's a constant. Now, if we were implicitly differentiating, that would be a problem. We would have to invoke the chain rule and do all of that stuff. But for our purposes, we treat the y as though it's a constant. Okay? So we just do it term by term. So all that would be is y remains. 6 remains, 6 square remains, y remains. So in this one here, with respect to x, we come to the first term in the expression. 2x squared is going to become 4x. Minus 3xy has an x in it, so we have to process it, which means the 3 and the y, as far as we're concerned, are constants. So the constants will remain. So the constants within the first principles differentiation. So we'll end up with 3y. And then we've got this one here has no x in it. So what we're asking d dx of a constant. Okay? In this case here, we're asking d dx. Now I know it's counterintuitive, right? Because you want to process it. You want to do something with the d dx. But this one is 0 also, because it's with respect to x. That's just a constant as far as the x function is concerned. Okay, so does that make sense to all? Yep. So when we just go through, and I'll keep doing them, obviously I'm not giving up on you, but yeah. Okay, sorry, I was just checking something. Alright, so what we'll have is 4x minus 3y for the x constant, so that's our solution for this one. And for this one here, we treat this thing like, I'll just change the colour. We treat this thing like, oh, okay, this time that's a constant with respect to y. That's a constant, so the derivative of a constant is 0. So 2x squared with respect to y is 0, so that term's zeroed out. Okay? Minus 3xy, I know it's very confronting, minus 3xy, we're doing it with respect to y, so that we have to process that as a differential, but the minus 3x will remain as a constant. And of course, plus 4y squared is going to give us 8y. So we process this as a differential. So just term by term, it's not too bad, is it? All right. So for part B, I'm just going to move my window here. There you go. Okay. Alright, so the next one here is part B. Alright, so are there any questions about that? You happy with that? So for part B, we've got a function g of xy, so it's just a change of pronumeral. So that's annoying. G of xy. And it's a sign. Now what do we notice about this? This is going to be a chain rule. Okay, so a genuine chain rule. Now the chain rule will have to be operated on inside the brackets twice, both for the partial with respect to x and the partial with respect to y. So what we'll do over here is we'll let u equal 2x plus 3y, and then we'll have two sets. One is the partial u with respect to x, but down here we'll have the partial u with respect to y. So I'm doing them both together. Okay, so what we'll do is we'll do the partial with respect to x in the first one, so this term here will be a constant. So the derivative of a constant is 0. So that term in this line here disappears, and we're processing 2x. So 2x will just be 2. For this one here, when we come to do it with respect to y, the x term is now a constant. And so from the differential, we're just doing 3y, and the differential of 3y is just 3. So it's not mixed up at all. Now, we used u here, so instead of writing two-value function, I'm just going to do the expression idea. Okay, I'm just going to do the expression idea. So I'm going to say, let's do the partial with respect to u. So there's the expression idea kicking in. Because it's too hard to write g in terms of u, I could write g of u. Okay, but it'd be dg du. I could put g there with respect to u, but then you might ask, if I do that, you might ask, well, where's the x and y gone? So in this case here, we can just not worry about it at all and just do the derivative u. So that makes that nice and neat. So we get the derivative of sine is cos, and so we get cos all of that stuff, 2x plus 3y, just like we would for our normal differentials. Same here, same again really, d du, so I'm repeating myself, I don't need to do this again, but you know I'm the long way idiot, so I'm going to go the long way, and so we're going to get cos 2x plus 3y for both sets. Now to chain them together, if we chain them together, d dx is what, partial with respect to x is what we wanted. We'll still have the partial with respect to x, we'll just go through something else, and the something else that we'll go through is u. So we go through u, so we've got cos 2 times cos 2x plus 3y. So this is the, for me, in terms of being a maths teacher in a high school, being able to do the chain rule is like your competence. It's like your #1 skill. Okay, so if you've got the chain rule down pat, you've got a big part of the maths problem in calculus sorted out. Very quickly here, we're doing with respect to y. We're still going to have it with respect to y. Something else. So we go through u, and we get y, and so in this case we'll get 3 cos everything else. So this one here is 2 cos 2x plus 3y, and this one's 3 cos 2x plus 3y. Alright, how's that sitting with us? Is that digestible? Is there anything you want me to go back over? Because now's the time. No judgment here. This is a safe place to learn. Mary Copeland told me I taught her that. I was pleased. I think it's probably the only thing I've taught her. A safe place to learn, which means you can ask any question, because this is we're maths mates together doing stuff, mathsy stuff. Okay, so you happy for me to move on? Pull me up if you need to clarify something. Okay. So for C, it's a 3-value variable. So for a 3-value function, what we've got is x, y, and z. And so we'll have to do 3 lots of that one like we just did. So we'll do the partial with respect to x, the partial with respect to y, and the partial with respect to z. Now if the pronumerals change, if they're RST or anything like that, you just basically do the same thing. So this time we've got to do the chain rule, so I won't repeat it twice now, I'll just do it the once. Equals x, y, z, and we'll d to u sine u, which would be equal to cos u. So we'll repeat that 1, 2, 3 times, because that's the first part of our chain. So this one here we'll get the partial u with respect to x, the partial u with respect to y, and the partial u with respect to z. So in this case here, partial ux is going to be, y and z are constants, so they'll remain. The partial with respect to y, this time it flips. X and z are now constants, so they'll remain. X and z, and then the last one z, x and y are constants, so they'll remain. And then all we've got to do is just make sure we do this character properly, z squared, and it'll only turn up in the last one. So let's do the derivative to this guy using our other stuff over here. So we've got yz cos x, yz. Now z squared is a constant as far as x is concerned, so that term goes. For x, gone. So all we're left with is yz cos x, y, z. Is that right? yz, xz. And then we've got, for y, again, the z squared is gone. It's a constant as far as y is concerned, so it's out. So we don't include it, but the rest of the chain we build up. So we're going to have xz cos xyz. And then the final one, which is z, this one does count. So z squared is going to become 2z, so that's that term. And we chain rule on the second term, so we're going to have plus, because the plus was here. Now it's x, y, cos x, y, z. And that's the I mean, when you walk through it, it's not so bad, is it? It's just that when you get it yourself, it's like, and maths is like that. You know, you're going to have multiple occasions, and this is where the reason I'm saying is because I don't want you guys to give up, because I know that you'll get hit with these moments where you think, oh God, I'm not cut out for this. Yeah, you are. You're exactly the right person to be teaching mathematics. So hang in there. No matter what happens, just keep walking. Okay, keep doing it, because you can do it, and maths needs you. Maths needs you. Okay, so just hang in there. If you get maths likes to kick us around a little bit. All right, and it does it to all of us. So there's nothing new in that. But if you're patient and take your time, what you'll find is that you know, you'll come to terms with everything. All right, enough of that. So we've got, how did we go? We got that one. All right, so we've got to do this one. So D. Okay, so for D we've got the function yz. So a bit an unusual one, but there you go. And it's y over z. So we'll do the partial with respect to y. So that's unexpected, but that's okay. And we'll do the partial with respect to z. Okay, we don't have to worry about a missing pronumeral, x or anything like that. As far as we're concerned, it's two functions in y and z only. Okay, so it's across and up only. Alright, so we can split this out as a product if you want to make it easier. We could do this as y times 1 over z, and that would just help you see the constant nature of the differential. That's like having, you know, this kind of thing. So in this case here, when we do the differential with respect to y, we don't care about the constant. 1 on z will remain as 1 on z. So we actually only dy the y, and so what we end up with is that becomes a 1, so all we're left with is the constant. Okay, always gets a bit nervy, doesn't it, when it's that thing there. So with respect to z, in this case here, we are going to deal with z, and y is a constant. So what that means is the y will remain. Okay, so what we'll do is we'll process this as z to the minus 1. So when we come to do the z now, it'll be, I'll just separate it so it's obvious, minus 1 out the front, and I'm actually doing the differential. Okay, so we get minus z minus 2, which is going to be minus 1 over z squared. And all of that together will be minus 1 over z. So this one here will be minus y z squared. Okay. So yeah. Alright, how do we go with that? That's question 1. We're done, I think. Yep. Any questions about that? Happy for me to keep going? You guys are so, you know, turn your microphones on and scream at me. You're so good. You're so quiet. It's like, come on. Alright, so 2. Okay, so for this one here, they want the partials in x and y, and the two-valued function is e to the x squared plus xy. So that looks like it's going to be a little bit interesting. So we want to do partial with respect to x and partial with respect to y. So we've got to let u equal x squared plus xy, and so we'll have a partial of u with respect to x for this line, and down here we'll have a partial of u with respect to y for this line. Then the other part of the chain is the front part of the chain, which will be our partial with respect to u of e to the u. Now how good's that? How much do we love that one? What's the differential of that one? Dun, 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 dun. You won't even turn your microphone off for that? Come on, that's the one we love.
It's A to the U, isn't it?
There you go, you're a genius.
Yeah.
Right? It's going to take you a while to get used to getting over what you've got to trust this process that I've taken you through. Right? These things that I've told you about, they work. They just do. So yeah, just work them. Alright, so this one here, we've got to do it with respect to x. So we've got to do this term, so that's going to be 2x. And xy, it's x by itself with power 1, so we're just left with y. It's hanging around there as a constant. Okay, and this one here is going to be with respect to y, so that's a constant as far as it's concerned, so it's gone, so we're just left with x. So we end up with 2xy e to the u, which was x plus xy, and for this one here we get x e to the x squared plus xy. Sorry, I'm just feeling with something. I want to check something. No problem here. Alright, so any questions about that? Are we happy with that? Okay, so we can move on from there. Now for part B, often it'll be a little bit tricky, won't it? So for part B, alright, so we're doing y to the power x. So our f of x, y, I should change that, is y to the power x. And we want well, we could do both, but why don't we just do the one of them? With respect to x, because that's all it really asks for, isn't it? df dx I'm looking at. And so here we've got our friends again. We've got our parts. Now, what are they saying here? Does that make sense to you? Is that making sense to you? They are saying that they're the same thing, and we have to know our log laws for this to be true. Okay, now we're looking for, now this is the pattern of thinking that takes hold, we're looking for undo. And we know undo with these guys has this form. It must have this form. There's nothing in the middle here. Okay, nothing. And yet what we've got up there is exactly that. We've got this guy here. So what do we do with it? Now this is why I love mathematics, because there's only one way to go with this. It's just a rewrite. Now the log law that we're interested in is to say that the log of a to the power b is b ln a. So the b is coming out the front. Their equivalence. That's the log law that we needed to check with. So all this means is that this is a rewrite of this right hand side. We're going to put the x up as an exponent on y. So e to the ln, because we're only treating this top term ln of y to the power x. Now they're the same thing. Okay, They're the same thing. And if we look at that, that is undo now, and we've got y to the x. Oh, y to the x does equal y to the x. So this part is about forms. It's about the forms of the expressions. Okay? It's just the same thing. So that's the kind of thing that a student will be troubled by. If you put it in one form, if it's just a change of forms and they don't recognise it, then yeah, that can be a bit tricky. Alright, so what we'll do here is we'll do the ddx of x ln y. So let's do that. Now, without any, so there's the blank page, right? The hint has been given. So really what the hint is saying, rewrite this in the other form. Now that's very hard to do. That's a university step more than it is a high school step, but in saying that, I'd probably bargain that into a 4-unit or an extension 1 type situation. All I would do here is change the form. They are the same thing. That's a big deal, right? That's a big deal. So it's probably on an extension 2 type scenario. But with the blank piece of paper, you're then expected to rebuild the question using the other form. Now we can do all of the other stuff that we do. And we do the partial with respect to x, and so the partial, this is now constant. The ln of y is a constant. Isn't that annoying? The ln of y is a constant. X is going to go, and so we'll be left with this. The partial of the expression that we've put up is just e to the u, e to the u. So our chain is going to be the ln of y, e to u, which was x ln y. So the differentials of exponents, it's very confronting. If I were to just do that in the staff room and say, oh, you've been practicing your differential expressions, and I gave you that, I'd expect you to slap me in the face. Like, seriously. Okay, because that's nasty. That's a differential, and you may not have encountered that. That's a university level idea. Okay, it's a very simple thing, isn't it, to have an exponent like that? But then what this is really saying, I want you, and even if I put it some other way, I want you to show me the differential of its equivalent form. And it's really confronting, isn't it? Its equivalent form. Okay, and you had to do the gymnastics to recognise that it was in fact the equivalent form. Okay, so please just take that with you, because I know people can be very smarty at school and try and catch you with stuff, but we've learned a couple of important ones, and this is another important one. Okay, that's a big one. Be careful. Okay, we did that the other day. We did do that, didn't we? Yes. So there's a couple, right? Any differentials of a logarithm are going to require the alternate form. So it wouldn't matter if it was what the form is, what the expression is, it still needs this kind of other form, this step, that you would have to do on your own. But that's not for school students per se, I think. But certainly the explanation is there. Alright, so are you happy with that? Yeah. Alright, so I think it was only asking for the FDX in that one, so that's good. We could do the Y part, but you can see what's going to happen. The differential, the ln of Y is okay, it's 1 over Y, so our part here would be, okay, alright, am I still on? You guys see me okay? Yep, sorry, I'm just having a little, yeah. So if I were to do the other ones, if that ever happens, what I'll do is I'll just come back on. So the partial with respect to Y would be x ln of Y. X would be a constant, so it would be just ending up being x over Y, because the differential ln of Y is 1 over Y. So this one here would be x over Y, e to the x ln Y. And if you want it to be cheeky, you could say, you can put them back in their other terms, by the way, y to the power x. You could do that here too, ln of y, y to the power x. You could do it like that as a product, because it is an equivalent. It's an equivalent after and before the fact as well. Alright, so watch out for differentials of exponents like that, where the variables come together. It would be the same kind of thing for 2 to the power x. Can I just pause and explore this? Yeah. Okay, so if you get y equals 2 to the power x, what would be the way, what's the equivalent of this one? Now, the way that I've couched that is a bit counterintuitive, because what we can do is do the log of 2, but if I do d dx of 2 to the x, that's a bit, because with this one here we can take logs. We can take the log base 2 for both sides, and that we've learned that, right? And that bit is undo. Okay, and so that would give us log base 2. Now that doesn't help us necessarily, so we've learned that from the calculus, the Ian Learning inverses sheet. We learned that, but if I couch it like this, how do I get, what's the equivalent? This is asking you the blank sheet equivalent. It's saying I need you to do this in its blank sheet equivalent form. Okay, so what it's going to be doing, and the clue is up there, but it's going to be saying put in e, okay, to the x ln 2. Okay, e to the x ln 2. Now that's hard. This is a much harder thing. So please be careful what you put up on the board with your advanced classes, because we can get very excited. We can say, oh, that needs to change a form. That's beyond them. You're allowed to say that. Now you've come to uni and seen this maths. Some of the stuff is obviously beyond them, but this nuanced bits and pieces here, that's a bit. So if I were to do this one, I'd go let u equal x ln 2. We'd have a partial with respect to x, and so we'd be left with the ln of 2. We'd have e to the u, which is e to the u. But look what's going to happen as a result. We're going to have ln of 2, e to the u, e to the x ln of 2. And we know that's equivalent. That's the ln of 2 multiplied by 2 to the power x, because they're still equivalent. So this form change is a big idea and can be very confronting if you encounter it in somebody's throwing it around. Okay, so just be mindful of differentials of exponents require an understanding that you're going to change forms. Okay, this trips up our students. You can imagine this, right? Students coming into first year and getting a differential of a logarithm or an exponent. It's very confronting for them. Okay, so you can do that in your sorry, I'll just grab this. So we want to do d dx 2 to the x. So we're differentiating 2 to the x. And there it's put the equivalent form, 2 to the x log 2. Okay, 2 to the x log 2. So if I were to change that to y to the x, which was our question, it'll come back with y to the x log y. And now you know why, okay? Now you know why. So, yeah, it's just something I thought that I should draw out for you. So differentials of these guys, be careful. All right, you can have a practice if you wanted to do one. You could do this one for me while we're talking, while I'm playing around. All right, let's see what you can come up with there.
A quick question. Would this be like part of the 4-unit course or?
I think it could be, yeah. It's been a little while
It's
since
just
I've. Yeah. It's just that form change, and so much of maths is recognition. I used to preach that all the time. Recognition. The students that I've got at the moment, I still tell them the reason you're pulling up a blank. It's okay to pull up a blank, right? It's like, well, I don't know what to do. I don't know what to do. And of course, what happens in maths, I think, is even from like year 7, 8, I'm pulling up a blank. Oh, it must be stupid. I hate this. I don't want to do it. And that's the thing that's hard to break, right? But once they realise is, oh, that's telling you something. That's informing you. That's saying the way that you're thinking about or what you're recognising needs a bit of development, right? So the forms idea, the forms of equations, I think it largely falls down to the forms of equations and how to rejig them. How did you go with this? How did you go with this one?
I just asked that because I was doing the micro teach. I was just doing the first one, and then I found a question in the 3-unit paper, one of the 3-unit papers that use this.
Yeah.
So yeah.
No, that's probably right. I have so much stuff swimming around in my head. It's hard to narrow it down to a particular topic that I can think of. But often what happens at school, in the desire to make students sweat a little bit before the actual HSC, they'll get harder exams. So they'll come out of trials and half yearlies and stuff and go, oh, I don't know what I'm doing. I don't know if I should be doing this. I'm going to drop it. You know, they have a panic attack. And in a way, that's a good thing. But that happens everywhere. Every school does that. They load them up. And so when they get into the HSC on the day, it's like, oh, that wasn't so bad. Which is a horrible way to prepare them, I guess, when you think about it. But
Yeah, because in a way, like I spoke to a student on the weekend actually, and she just did her trials, and she was really feeling really bad. She was like, "Oh, I just barely passed my advanced paper," and I said, "Look, I said, don't worry, but it's really like, I guess it depends, but they do make it really hard." And I've just seen our standard paper, like our year 11, and we bought it, and it's extremely hard. Like I think all my students are going to fail it.
yeah. And I think the
It's
thing is, it takes a long time, Tricia, to prepare a group for a bought paper. You know, and what I mean by that is you get them, if you get them in the beginning of year 11, if you've had them in year 10, all the better. All right, this is why it's good to get them in stage 5, so you know what's coming up in a couple of years' time. If you can manage to have that, often you're not, you're just shoved on it. I had a hard one once. I started at a new school and took over the year 12 class. And I was like, oh my God, what a confronting thing. Because the styles were different, the preparation was different. the teacher had gone to another school, and it was like, oh no. So yeah, it is confronting. What can you do? You just got to realise that there's no quick fixes, and it's not a lie. It's not a lie to tell them just hang in there and keep being positive. Look, the opposite to this. This is what you're faced with, right? I test all the incoming students that come. Now, with COVID, we've been doing it online, but they used to come in, and I'd see hundreds of students every day until we got through the testing. And one day I had this young lady come, and it doesn't matter that she's a lady, and it doesn't matter that she was a pretty kid. It doesn't. That's not important. What was important is that she was a performer. She was someone who had a performance, and she got a good ATAR. She got about 95, I think. She did really well, but she was encouraged by her curriculum coordinator to do general maths. And she sat down and did my test and came back to the desk, and she was livid. She was actually livid. She wanted to do a science degree, and she couldn't do it. She was filthy. So I would rather have the student standing in front of me, your student that you just mentioned, I would rather have that student standing in front of me who's had some curriculum experience in that subject, as opposed to this other young lady who was just, I think she might have even changed courses or something, but she was absolutely livid that she'd gone and ticked all the boxes, done everything that all the adults had told her to do, and there she was not able to do this entrance test for a Maths 1 subject. She was filthy. So that's convinced me, this experience at university has convinced me we do no harm when we encourage a student to hang in there. Okay?
Yeah. And I've actually had this conversation with the year 10s because I teach the top year 10 class. I job share, but there are a lot of really strong, like a few of them are doing extension next year, a few of them are doing advanced, and they all want to do engineering degrees. But no one from careers has actually spoken to them about the prerequisites for the engineering degree. So I'm just literally going off what I know from UTS, and I'm like, guys, you're going to need extension, you're going to need advanced if you're doing that. But our school is tending to funnel most of the students into general, like standard maths, because they'll prefer them to do better at standard and get a high ATAR.
This is the problem, isn't it?
Yeah.
This is the problem. This is one of the things that weighed on me heavily. So when you've got to be careful how this cultural thing impacts on you. I'll just check my time of my video. Sorry. That's just okay. Oh, actually, I might just quickly stop it.